Hello, everybody. This is a recording of a short introduction to Chapter 2, Degrees of Freedom. The purpose of this recording for you to watch it before I actually teach the entire topic in the class. And also it helps you to prepare for the upcoming quiz on Friday. And also you should be able to do your assignment 1, which is due this Sunday after watching this lecture. All right. Let me share my screen and then we'll start from there. Sharing my screen there. Okay, the screen is being shared. I'm gonna also turn off my videos because you don't need to see me anymore. We're just gonna focus on the lecture. All right. And seems to be ready. What is the degrees of freedom? As the name implies, the number of freedom that a mechanism has or a component has. All right. Let's start with a very, very simple example. Let's say that you have a box and this box is in the screen. All right. So if somebody asks you how many degrees of freedom this box has, most likely you would say it has 3 degrees of freedom because it can move left and right, ups and down, and also it can rotate, right? So you may also say that it can go like in an oblique direction, which is true, but always we say a direction like that one is a combination of X and Y. So in simple word, we say this box in the screen, all right, has 3 degrees of freedom, can goes ups and down, left and right, and it can rotate. Okay, so we'll show them by some, let's say, axes. We'll say it can move in the X direction, it can move in the Y direction, let's call that one Y direction, and we say it can also rotate, let's say rotate in a rotation like that. Or maybe I should show it better in rotation like that. And if we want to put some parameters, we'll call it X and Y and theta. Okay? So we'll say that the degrees of freedom for this system is equal to 3. All right. Pay attention for simplicity. I show the degrees of freedom or an abbreviation for DOF by just simply F, meaning freedoms. It's just to write our notes easy. Now the same box, let's say I copied and I put it here. But this time, this box, let's say that we constrain its motion and we put it inside. Maybe if I do a better job for you, let's say here. Move it a little bit up there. And okay, so we'll put it inside, let's say, a rail or a channel. And that channel, as we said in lecture 1, when we use this dash, it's a symbol for saying that it's being fixed. Now, if I ask you the same question, what is the degrees of freedom of this one? You may stop the video at any point and answer my question, but you should be able to say that this box can move only left and right, all right? So it means that the degrees of freedom now is only 1. So what happened to other 2 degrees of freedom? Remember, we said this box has 3 degrees of freedom. Here, we notice it has 1 degrees of freedom. So we will add that we added some constraints. We show the constraints by the letter U. There's nothing to do with constraints. We should show it by C, but we reserve the letter C for later use. Okay, so we'll be happy with U for now. All right, so please pay attention to the notation here. We show the freedoms by F and constrained by U. We said that this box used to have 3 degrees of freedom. Now it only has 1 degree of freedom. It means that something stole 2 degrees of freedom, which we call them constraints. So in other words, these walls or these rails created a U equal to 2. All right? And we also should pay attention that always U plus F, always U plus F gives me 3. All right? Let's consider another example. Let's say I have a link, like my pen, my pencil, right? How many degrees of freedom it has? Again, you can stop the video at any point and answer this question. So your answer should be 3, because similar to what we had for the box, this link can move to the left and right, ups and down, and it can also rotate. So it has 3 degrees of freedom. Now the same link, let's say I join it to the screen. So I use a pin and I join it like that to the screen. So this is a joint. Okay. Now, if I ask you how many degrees of freedom it has, so obviously this link now cannot move left and right, ups and down. Perhaps if this is the vertical line, we notice that it can only swing. All right, of course, left and right, it's obvious. These things can swing left, right, left, right. So what we say here, we say that this X freedom, Y freedom gone, only left with 1 degree of freedom, theta, right? So it has 1 degree of freedom. Therefore, we say that this little joint created a U equal to 2. Because remember, always U plus F must be equal to 3. All right. Let's now make it more interesting. Let's say I have a link here. I have another link. And let's say I have a box. All right. So each of them are free, and we know this link has a degrees of freedom of 3. This link has a degrees of freedom of 3. And this link has a degrees of freedom of 3. So we say the total degrees of freedom that we have for each of them is equal to 3. Now, let's assemble them together in a simple mechanism. So I copy this link and I put this link there. And I put that link there as well. So if you managed to attend the lecture 1 and I showed you a software there and you saw in a simulation how we managed to join these links. So let's say I join this one to the ground. And I join these two together and I joined this link to the ground as well. Now let's also constrain the motion of these things there. All right, so we'll do that, that, and that. And this dash means the constraint. All right, so just for simplicity, let's number these links rather than calling them. So 1 always we said in lecture 1 is ground. So link 2, 3, and 4. We know the degrees of freedom of this mechanism, degrees of, let's write it down there. So this is 1 there. So the degrees of freedom for this mechanism is equal to, we know that we have 4 links, right? Link 1, 2, 3, 4. Each link has 3 degrees of freedom, right? Go back to the left side. Has 3 degrees of freedom. This has 3 degrees of freedom. It has 3 degrees of freedom. But wait, what about the ground? Ground, it doesn't have any degrees of freedom, right? So then I subtract it from 1. So meaning that we don't care about the ground. Total number of members minus 1. And each has 3 degrees of freedom. So this is the degrees of freedom, but also we learn that now these members, they are not free. There are some constraints here. There are joints. We just learned that this little guy, this little joint here, it creates a constraint of 2, right? It was just up there, the joint create a constraint of 2. What about this one? U is equal to 2. And what about these other joint here? U equal to 2. So, and also this constraint here is equal to 2. It's very similar to this box there. So in other words, I had so many degrees of freedom, but unfortunately, some of these joints and rails, they stole the freedom and added constraints. So I have like 2 constraints plus 2, plus 2, and plus 2, right? 1 here, let's count it again. Another one there, another one there, and another one there. So it gives me 1. So it means the degrees of freedom of this mechanism is 1. What does it really mean? It means that if I have only 1 piece of information for this mechanism, for example, if I know how fast this link is rotating, I should be able to find out about the speed of link 4 in future topics. So degrees of freedom of 1, it means that 1 piece of information is good enough, like a speed, an angle, to find out the rest of information about this mechanism. For example, if I know the speed, or if I know this angle, how this angle is changing, and so on, it's good enough to learn about this mechanism, all right? So similar to that pendulum here at top, if I know this angle theta, that's enough for me. I can analyze it, okay? So let's just do a few more examples. And again, don't worry, we're gonna do more examples in the class in an actual lecture. This is just a very, let's call it pre-introduction for you to watch and stop and analyze and think about it in more details. Let's have fun with just maybe a disk. Let's make it more interesting, this disk. Maybe I'll do a little bit of that for you. All right. So I have a disk. This disk, all right, it's more like, let's say, a coin. And it is flat on the screen. And if I ask you how many degrees of freedom it has, you should be able to say, well, it can move in X direction, it can move in Y direction, and it can also roll or sorry, rotate. So in other words, it has like X, Y, and theta. So you should be able to say that it has 3 degrees of freedom. Now, let's just put the same disk on the ground, a kind of flat ground, and right, it's there. Now, I'm just going to claim for now that this disk can only roll. Like it roll or it's rolling without a slippage or without the slipping. What does it mean? So I want you to visualize your car or somebody's car moving on a street. In a regular motion, the wheel, it just rolls, right? It just rotates and rolls. But imagine that somebody is moving fast, all of a sudden, they put on a brake, and they have to stop. So you know the car is not going to stop immediately. It's going to create actually a track on the ground, right? In other words, the wheel is going to rotate and sort of slip on the ground, right? It's not just pure rolling. Okay, that's a different scenario. But let's just focus on the rolling for now. If there is only rolling, okay, that's scenario number 1. Let's save it for later. Scenario number 2, or you know what? Let me just make more room for myself. Bring it this one down there. I need to be careful about other things that I'm going to put on this slide. All right. So 2 scenarios. One scenario that it rolls without a slip, and the second one, it rolls with a slippage. Okay, what's the difference between these two? Scenario number 1, and again, we'll come back and discuss it later. When it rolls, if it has a motion, let's say X there. Let's call this one X, and this rotation theta. Later, we'll come back and we prove it actually. These X and theta, they are related. X actually is always equal to R theta. All right. So in other words, this system, when it rolls, I do not need 2 pieces of information. I do not need X and theta at the same time. If I know one of them, I'm good to figure out the other one. All right, so we're going to highlight this one so we remember it, that X is always equal to R theta when there is no slippage. What about the other scenario? Unfortunately, here X is not equal to R theta. This is X and this is theta. And again, we're going to come back and we're going to prove that. But for now, let's just accept it from me. So it's not equal. Okay? So now let's get to our idea of freedom. In scenario number 1, we say the freedom of this system is just 1. Because one piece of information is good enough to learn about this system. Either if I know X or if I know theta, I can learn more about this system. But here, I need both X and theta at the same time. So the freedom of this system is 2. Okay, so you may say, oh, wait a minute. This disk, by the way, it can move, jump up right? But we assume that this disk and the other one, they are always touching the ground. So let's say there is some sort of magnetic force and they are always touching the ground, okay, if they are not separating from the ground. If they are not separating from the ground, it means they have no y motion, okay? The original disk had x, y, and theta. These two disks, they are sort of, let's say, have to stick to the ground, but they can, one of them can roll, maybe because of the weight or weight of the car or something. They always touch the ground, okay? So there is no y motion. The first disk can move to the right or left and can rotate. The other one, the same, can move left and right, can rotate, but the first one, x and theta, they are related. The other one, they are not related. So that's why we say that the first one has a freedom of 1, second one has a freedom of 2. So we're going to summarize what we said here. We're going to say whenever you have rolling without a slippage, it means you are constraining it by 2. Remember, we said always F plus U is equal to 3, always. The first one here had no constraint, 0. This guy has a constraint of 2. What about this one? You should be able to guess what is U for this guy. Always U and F, their sum is equal to 3. So U is 1. So whenever you have rolling with a slippage, just assume you have a constraint of 1. U is equal to 1. Otherwise, your U is equal to 2, like the scenario here. Always in the problem, we actually clearly and explicitly state that if there is rolling without or with a slippage. So it's nothing for you to worry, because we will say it in the problem if there is a slippage or there is not. Let's have some fun, make a mechanism. So I'm going to add 3 components here, and we're going to see how they are going to work out as actually a mechanism, all right? So let's just move them a little bit. This one here, that one there, and this one there. Okay. So each of them by themselves, they have degrees of freedom of 3, 3, and this guy has degrees of freedom of 3. But let's make a mechanism out of them. I'll move that one there. And I move that one there. Okay. So now let's join them together. So this is one joint here. This is, let me just make it a little bit nicer. All right, a joint there. So from what you learned in lecture 1, this is a linkage. A linkage, it means also it has one free members. That free members we can pretend is just this member there, which is the ground. So we'll fix that ground. So this is the ground there. And we say we don't typically show this ground there. So why not? We'll put this disk on a flat surface, sort of to have a meaningful mechanism there. Now we have a mechanism. Let's number these mechanism, the number of linkage that we have. So 1 is the ground. This is member number 2, member number 3, and member number 4. Our goal here is to find out the degrees of freedom, DOF, degrees of freedom for this mechanism. Okay, so let's just do what we did earlier, for example, above. We said we have 4 members in this mechanism. One of them is the ground. You always subtract the total number of members, total number of members. And -1 is ground. We always have one ground. Okay. And we say each member by itself, we claim they used to have 3 degrees of freedom. So it means now I have to multiply it by 3. But we have constraint, -1 constraint for this joint, 1 for this joint, another constraint for this joint. And now wait, what's going on here? So as I said, the question should tell us what's the scenario here. In this problem, let's assume it says roll without slip. So roll without a slip, it means here I have u equal to 2. So as you see, I have how many? 2, 4, 6, and 8. 8 u's there. It gives me a degrees of freedom of 1. What does it mean to have a degrees of freedom of 1? Well, degrees of freedom of 1 means that if you just have one piece of information for this mechanism, let's say if you just know how fast this link 2 is rotating, you should be able to find out and figure out that how fast this disk 4 is moving to the left, which is a topic that we will do it in chapter number 3. All right. So let's summarize what we said here in a nice clean formula, and I'm going to write it down on the corner here. Okay, so we managed to find a very important formula. Degrees of freedom is equal to 3 multiplied by n minus 1 minus sum of u. Now it looks a very interesting, and you may say even a sexy formula, right? So what are all these scary parameters? N is the number of members. U, constraints. And of course, you learn from math, this means sum. Okay, so looks like a scary formula, but it's not, right? It's not actually a scary formula. And let's put it inside box so you can remember it. Okay, now we're going to use this formula and solve some example together so you see how simple it is. What is this? A 4-link mechanism. If you forget what it is, please go back to lecture 1 and just review it. It's a 4-link mechanism. I want to find out the degrees of freedom. Degrees of freedom is 3 n minus 1 minus sum of u. Always that's the formula. Okay, my job, know the number of members. 1 is ground, 2, 3, 4. Minus 1 minus number of constraint. Every joint that I see here is a constraint, all right? And so let's just raise that one. So I'm going to highlight the joints. I have 1 joint there, 2, 3, and 4 joints. Each of these joints, they create, we know, two constraints, all right? So sum of all those things there, all constraint, is 8. Oh, look at the second mechanism. It looks like a very complicated mechanism. What is the degrees of freedom of this mechanism? 3, 7 minus 1, minus, and I let you to count the number of U's. Okay, you may stop the video, but I'll do it here. 1, 2, 3, 4, 5, 6, 7, 8. So 2 multiplied by 8. And let's do the calculation here is 2. All right. So let's just stop here. Make sure that we understand the meaning of these numbers. Okay. These numbers are important for later when we want to design this mechanism, when we want to analyze this mechanism. For now, we'll just get the numbers. Whenever we say the degrees of freedom is 1, it means this mechanism, it just needs one motor to turn it to a machine. If I attach one motor to link 2, and then I let it to rotate with omega, then we say this is a machine that works perfectly with no problem. So it means degrees of freedom 1 means I just need one input. All right. We just need one input to move this mechanism. All right. What about the second one? Second one, it's 2. What does it mean? It means if I put a motor, let's say here, and I give it omega, okay? And typically, in order for us not to get confused when we have complicated mechanism, we'll call this one omega 2, meaning the motion that we give to link number 2. Okay, now somebody asked me, can this mechanism function properly? Our answer should be no, because one side of this mechanism, the left side may works fine, but the other side, it's just going to be loose and maybe fall apart. If you don't think it's going to happen, later, using the same software that I showed you in lecture 1, and you're going to learn to use that software, you're going to build actually the same mechanism and see it's not going to work properly. So you need another motor wherever you want to put it. And of course, you may decide to put your motor, let's say there. So we call that one omega 7. Okay. So now, if somebody gives me this mechanism, and of course, beside the size of this link, tell me what is omega 2. Let's say it is 10 radian per second. And what is omega 7? Let's say it is 25 radian per second. I should be able to figure out what is the speed of, let's say, point A, or what is the angular velocity of link 5. We call this omega angular velocity, but that's a topic in chapter 3, which we will get to that in more details. All right. So please stop here. Make sure that you understand these two examples. It's very, very simple. And again, as you see, we are going to use always the same cool or sexy formula that we found it together before. All right, let's just solve a couple of more examples and make sure that you understand all other details. Okay, so I have a simple mechanism here. The degrees of freedom, DOF, is 3. And 6 minus 1, this is a very easy part. part that I should not make a mistake is counting the number of joints. It's one there, one there, one there, another one there, and another one there, okay? So I say this is u equal to 2, u equal to 2. We don't need to in the exam to write that. It's just for me teaching you, and I emphasize on writing them. And as a practice, you should do that. But in the exam, if you just count them and you are sure that you didn't make a mistake, you don't do a mistake, that's fine. Now I want your attention a little bit on these three members there, which we magnify them over there also. The scenario is here that instead of two members being connected to each other, like 5 and 6, or 2 and 3, or 2 and 1 there, we have three members there. Whenever you see three members, in reality, they may connect like that one. You see, this is the joint there. So link 3 is being sandwiched between link 4 and 5, right? So you can think about it and visualize it. Maybe this pin is being attached to link 4, and 3 and 5 are just, there is hole in them and they can rotate. Try to visualize these connections. This is how three members are connected at one point. Whenever you see a joint with three members, remember that between each of them, you have two constraints. Between 3 and 4, you have two constraints. Between 4 and 5, you have another constraint. So in other words, let's not confuse ourselves. Whenever you see three members, your u is not 2, is 2 plus 2, or 4. Okay? So now let's count how many u's we have. We have 2, 4, 6, 8, 10, and 14. It gives me 1. So it means this mechanism has only 1 degree of freedom. Good news, if I know this omega 2, I can find out, for example, what is omega 6 later, of course. Okay. But the moment we know omega 2, we can learn about omega 6. We can learn about omega 4. Okay. We don't need them. We can find them just using this mechanism. All right. I'm just going to solve another example and leave the rest to you to think about them. And on Monday, we'll come back and resolve them together. I answer any question that you have. Okay. Please stay with me for this last example. Looks like a weird mechanism. Let's just analyze it together. This time, the question did not provide us with the number of joints, number of members, sorry. So we need to count them carefully. This is link number 1, or ground. Link number 2. This is link number 3. Be very, very careful. Link number 3. The entire thing is link number 3. And then what else? This is a link number 4. And also pay attention, this link number 4, like this entire thing is link number 4, right? And then what else? This is 5, and this box is 6. Remember from lecture 1, I told you we just out of laziness, we don't draw this upper portion, but it doesn't mean it's not there. It is there. We just don't show it. Let's just draw it there. Have a nice pictures there. Okay, so I have 6 members. So the degrees of freedom in this mechanism and is 3, 6 minus 1 minus. Now it comes to counting the number of u's. Let's do it carefully. So one joint there gives me u2. One joint there gives me U2. Make sure you don't get confused. There is only two members connecting there, right? Only two members, not three. Member 3 looks like two members, but it's not. So try not to make mistake. Just one joint between 2 and 3. So there's another joint there that we already talked about it. This is U number 2 attached to the ground. U number 2. U number 2. Joint there. U number 2. All right. Now we should not forget, whenever we see like a guide or rail or like whatever you want to call it there that prevent this box from rotating or going ups and down, it creates a constraint which is equal to, oh, I forgot, let's move back. Move back, move back, move back to slide number 1. Oh, it's here. Whenever we see this scenario, it means U is equal to 2, okay? So going back there. So it is U equal to 2. And it's coming from these walls. So let's count them. I have 2, 4. Okay, I should not make a mistake. 2, 4, 6, 8, 10, 12, 14. 14, 1. So this mechanism has 1 degree of freedom. Whatever this mechanism is, which later we will learn more about this interesting mechanism, it has 1 degree of freedom. You can sort of guess what this mechanism is. If I, let's say, apply load and maybe push these things up that way, it's gonna move that things that way. Or maybe I'm wrong, the other way, which we'll learn more about it later. So in other words, if I have an input, I'm gonna get a force output. But one input is good enough for this mechanism to work properly. And that's the meaning of degrees of freedom. All right. I'm gonna solve the example 4 and example 5, these 2 examples in the lecture on Monday, but I want you to think about them. I don't want to give you the answer right away. Think about these 2 and be prepared for the Monday. All right. I'm gonna stop sharing here. And I'm gonna turn on my video. Okay, it's getting dark here. I'm gonna turn on my light. Okay, it's better now. All right, please watch these videos and don't worry if you don't understand all of it. You didn't have a chance to ask question. This was, again, as I said, is just a preparation for this lecture. Please study it. I will also post the annotated slides for this recorded lecture. And this should be good enough for you to solve assignment 1, do your best to do that, and to do the quiz on Friday. I'll see you on Monday. All right. And don't forget, at 8 a.m. on Friday, you just need to log into Canvas and start the quiz. Okay. You have 90 minutes. Good luck and have a fantastic day.